to encode or store a small number of logical qubits. There are many quantum error correcting codes on the market. One of the most promising quantum error correcting codes is the so-called Z2 surface code. What makes the Z2 surface code particularly promising are that one, it has high error thresholds, so it is relatively robust to errors. Two, it is scalable, meaning adding more qubits give you better protection for the information. And third, it's fairly easy to implement. And instead of articulating the sense in which it's easy to implement, I'll just flash three semi-recent experiments which have realized the Z2 surface code in superconducting qubits on a neutral atom platform are trapped ions. So the Z2 surface code is great at protecting our information, but it comes with a catch, and that's that although it is hard for the environment to access the information, it is such that if you conjugate a Pauli operator P by the unitary, you get out another Pauli operator Q. So these are unitaries that map Pauli operators to Pauli operators by conjugation. There are also a number of measurements that can be performed natively in the Z2 surface code. In fact, we can measure any Pauli operator or product of Pauli operators in the Z2 surface code. Together, these gates and measurements constitute the Clifford operations. Clifford operations are fantastic. We definitely need those for quantum computing. However, they are not sufficient for implementing arbitrary operations or for performing universal computations. These Clifford operations can be efficiently simulated on a classical computer. For universality, we need something non-Clifford. We need to supplement the Z2 surface code with a non-Clifford gate or a non-Clifford state. And here by a non-Clifford state, I mean a state that cannot be prepared from an all-zero state using Clifford operations. There are a number of strategies for supplementing the Z2 surface code with something non-Clifford. The most well-studied is magic state distillation. It's not really important for this talk what is meant by magic state distillation, but what is important is that magic state distillation is notoriously resource intensive, and by some estimates constitutes the majority of the overhead in the quantum computation. Another approach is dimensional jumping. This is where we take information stored in Z2 surface codes, transfer it to a code in a higher dimension, perform a non-Clifford operation natively in this higher dimensional code, then transfer the information back into the Z2 surface code. This could work. It's a viable avenue. However, it does require that your architecture is able to accommodate three-dimensional quantum error correcting codes. In this talk, I'll focus on a third option, which is using non-abelian topological order to perform the non-Clifford operations. Now, typically when people talk about non-abelian topological order in the context of quantum computation, they have in mind creating quasi-particle excitations or anyons, storing the information in some internal space, and then braiding those anyons to perform the quantum computations. We'll actually take a different approach to using non-abelian topological orders to supplement the Z2 surface codes. So here's the overall strategy. We'll start with our information stored in the Z2 surface codes, and we'll perform Clifford operations natively with the Z2 surface codes. Then within the G surface code, we'll perform our non-Clifford operations. We'll spend as little time as possible in the G surface code, then transfer the information back to the Z2 surface codes. Now you could ask, why don't we just spend all of our time in the G surface code and this implement the measurements that are needed to operate the non-abelian quantum error correcting code? Second, the decoding problem is likely more challenging. The algorithm for cleaning up errors that as they occur is more complicated for these non-abelian topological orders. So you might as well just spend as little time in those codes as possible. This paradigm isn't new. We didn't come up with this. Um, here's a non-exhaustive list of papers that have come out use this paradigm of switching between Z2 surface codes and non-abelian topological orders. You notice there's one all the way back in 2018, and the last are just within the last year. Here's the outline for the talk. I'm going to start by reviewing the Z2 surface code. If you're familiar with the Z2 surface code, you can think of this as just setting notation for group surface codes. I'll then describe a set of elementary logical operations that we can perform in group surface codes. We'll compose these elementary logical operations to perform interesting logical operations in the group surface codes. I'll then show that we can bring this story from a spatial picture to a space-time picture. This will give us space-time building blocks, which we can glue together to perform our non-trivial operations. I'll give a few examples and conclude with some future directions. Before I jump into the Z2 surface code, let me just take a moment to encourage questions and comments throughout the talk. I wasn't sure what the audience would be like, so my excuse is for making this as broad as possible is that I'm going to encourage you to interrupt if there are any questions. Are there any questions so far? Yeah.
I have a quick question about the definition of a surface code. Does this imply the open boundary condition, or you still use the torus geometry?
So here's how we'll define the Z2 surface code. Yeah, it's rough and smooth boundaries.
I see. So, and for G surface code, is the
Yeah.
smooth and rough boundary the same, or you need to choose different geometry?
Yeah, good question. We'll get there. Let me build up to that through Z2 surface codes. But yeah, but specifically what I mean is a patch of Z2 topological order with rough and smooth boundary conditions or a G quantum double model with rough and smooth boundary conditions.
Yeah, thank you.
Any other questions before I move on? Okay. So the Z2 surface code is defined on a square lattice with rough and smooth boundary conditions. Rough here just means these edges end. And on each edge, we'll place a two-dimensional Hilbert space, a qubit. A basis for this Hilbert space can be labeled by 0 and 1 states. And the key operators on this Hilbert space are Pauli X and Pauli Z operators, X and Z squared to the identity, and X and Z anti-commute. The code space where we'll store quantum information is defined implicitly in terms of a set of stabilizers. There are two types of stabilizers. First, for the vertex stabilizers, these are a product of Pauli X operators around a vertex. Note that we've truncated this product of Pauli X operators along the smooth boundary. There are also plaquette stabilizers. These are a product of Pauli Z operators around a plaquette or a partial plaquette on these rough boundaries. The code space where we'll store information is defined as the set of states which are stabilized or invariant under AV and BP. And you can check, I'll prove this more generally for group surface codes in a moment, that the code space has dimension 2. Let me now move on to group surface codes. Again, we'll have rough and smooth boundary conditions. I'll implicitly assign an orientation to each of the edges. Horizontal edges are oriented to the right, vertical edges are oriented upwards. On each edge, we'll place a G-dimensional Hilbert space, where G is the order of the group. And because the Hilbert space has dimension G, we can label a basis by the elements of G. I'll introduce two operators here, LG and RG. LG acts on a basis state. by left multiplication by G. RG acts on a group basis state by right multiplication by G inverse. Is G inverse here so that RG forms a homomorphism? RG times RH is equal to RGH. Similar to the case of the Z2 toric code or surface code, we can define a code space implicitly in terms of a set of stabilizers. There are again two types of stabilizers. The first is a vertex stabilizer. This is a product of LG and RG around a vertex. The assignment of LG and RG is determined by the orientation of the edges. So LG if the edge points away from the vertex, RG if the edge points towards the vertex. Note that in general, these do not commute, because in general, we can consider a non-abelian group. They'll commute at neighboring vertices, but they'll fail to commute at the same vertex. AVG and AVH might not commute. The second type of stabilizers that we have are plaquette stabilizers. These project onto states such that the product of group elements around the plaquette is equal to 1. Here, this product is taken according to an ordered path, and whether it's G or G inverse depends on the orientation of the edge. So here, this checks G1 times G2, but here it's G2 inverse. G3, it's opposite, we'll go counterclockwise around the plaquette. If this counterclockwise path is aligned with the orientation, it's G. If it's anti-aligned, it's G inverse. So that's why it's G1, G2 bar, G3 bar, G4. The code space is then the set of states that are invariant under all of the vertex stabilizers and all of the plaquette stabilizers. In gauge theory language, AG can be interpreted as a gauge transformation.
In the whether the surface code support non-Clifford gates.
That's a good question. So it's a bit difficult to answer that question because what we mean by Clifford or non-Clifford depends on our encoding. So we ultimately need to be able to transfer our information from Z2 surface codes into this non-abelian theory, then back to Z2 surface codes to make an assessment of whether it's Clifford or non-Clifford. So I don't know how to just say in general this group has Clifford or non-Clifford. I need to also consider transferring information from some abelian surface codes, or I need to tell you what are the Pauli operators so that I can define Clifford and non-Clifford.
Okay, I see. Thank you.
But yeah, that's a very good question. I don't, for all the examples that I've considered now, I've only considered very simple groups. But I'll specify the class of groups that I'm considering, and I think you have to get pretty exotic groups to fall outside of this class.
Mm-hmm. Thank you.
Yeah.
Tyler, I have a related question. So you emphasize this is from the standard, this is different from the standard non-abelian topology that we can use S3 to perform universal unitary gate using the anion braiding. So you don't follow the traditional rule.
Yeah.
So yeah.
Yeah. Oh
So
yeah,
in this case,
this is
does
building off
S3
of,
work?
sorry, go ahead. Go ahead. Sorry.
So I just want to say, does S3 like default work here?
Yeah, S3 and D4 are both good examples. I'll use D4 as an example later in the presentation.
Okay. Any counter example, like what kind of group doesn't work here?
What kind of group doesn't work?
Yeah.
Yeah, let me get to the elementary operations, and then I can. A5 is fine, so it doesn't need to be solvable.
Oh, okay. Yeah. Thanks.
Yeah, but to make that statement a little more, to make the statement more rigorous, I'll need to get a little further into the text, or into the presentation.
Hello, before you do
Yes.
so, I also want to follow up. Do you mean whether this group surface code works still depends on how you connect the Z2 surface code and the group surface code?
Right, yeah. So if your question is, can it perform a non-Clifford operation? Non-Clifford isn't well defined unless I operations in an abelian surface code. So if once you have those Pauli operators defined, now you have to relate.
Okay, thanks.
Yeah. Okay, good. Yeah, thank you for the questions. If I don't finish the presentation, that's fine. At the end of the talk, the paper will appear, and so it's the continuity is all good. Okay, so what I'd like to do next is I'd like to prove that the code space has dimension order the group G. And the way I'll do that is I'll consider the set of flux-free states. These are group basis states, so it's just a configuration of group elements on the lattice, such that there's no flux. The BP, the plaquette term, is stabilized, is satisfied. So here's an example. This is a configuration of group elements. You can check by multiplying the group elements around a plaquette. There are no fluxes. This is, however, not gauge invariant. It is not invariant under applying the vertex term. But what we'll do is we'll organize these flux-free states into gauge equivalence classes. We'll say two flux-free states are gauge equivalent if there exists this flux-free state is gauge equivalent to this flux-free state. I can apply a vertex term here, and that removes these loops. In order to form code states, we can take an equal amplitude superposition over flux-free states over a gauge equivalence class. These will be flux-free because it's a superposition of flux-free states, and it's gauge invariant because we include all of the configurations in the same equivalence class. These furthermore form a basis for the code space. They span the code space since every flux-free state belongs to some gauge equivalence class. That implies that the code states must be superpositions over gauge equivalence classes. These are also orthogonal, since distinct gauge equivalence classes will give rise to orthogonal states. So this forms a basis. And that means that all we need to do now is count the number of gauge equivalence classes. So here's what I'll do. I'll consider a general flux-free state. This is just a configuration of group elements. There are no fluxes. And I'll argue that I can put this into a canonical form, which allows me to easily label equivalence classes by some nice representative state. What we'll do here is we'll try and push all the group elements to the right by applying gauge transformations. So first I'll apply a gauge transformation AG1 here. This acts with G1 inverse at this edge. So it'll move the configuration, it'll move that group element to the right. Then I'll proceed across this top row, apply AG1, G2 here. Then I'll move the group elements further. And I can go all the way across the top row, end up with some group elements on these vertical edges and an element G on the rightmost edge. I can do this in all the rows. So let me go ahead and do that. I apply gauge transformations in all the rows to move the group elements to the right. Now we use the fact that this state is flux-free. Since it's flux-free, the plaquette term is satisfied here, which means that the product of group elements around this plaquette should be equal to 1. That implies that G6 tilde was 1. Okay, now I can go to the next plaquette, and that implies that G7 tilde is equal to 1. We can go clear across the row, and in this last plaquette, we find that going around this plaquette, G times H inverse has to be equal to 1. If G times H inverse is equal to 1, that means that G is equal to H. I can do this in all the rows, and what I end up with is the messy configuration we started with is gauge equivalent to a configuration with the same group element on all the edges on the right. This is a representative gauge fixed state, and it's labeled by a unique G in G. It's unique for a reason that isn't important if it's unclear, but you can compute the, oh shoot, what's the word? Holonomy, sorry, the holonomy across this patch, and that's gauge invariant. So this labeling by G is unique. So you see the gauge equivalence classes are labeled by elements of G. So here's a gauge equivalence class labeled by G. It's represented by this configuration where all the group elements are on the right. This forms a basis. So the dimension of our code space must be equal to the order of G. We'll label the basis states by the elements of G, and I'll put a subscript L here to remember that they're the logical states. So what this state is explicitly is a sum over flux-free states in the gauge equivalence class labeled by G. And moving forward, it'll be convenient to work with the gauge fixed states as opposed to this superposition. So we'll just look at this nice representative state where all the group elements are on the right. What I'm going to do next is start introducing elementary logical operations for the group surface code. But let me pause here and see if there are any questions about this argument. Okay. There are three types of elementary logical operations that I'll introduce. The first are transversal gates. Transversal gates are implemented by a product of single-site unitaries on every edge. Extend and split. This allows us to take two group surface codes and merge them into one group surface code. It allows us to transfer information from Z2 surface codes into non-abelian surface codes. And then finally, preparation and readout. Let's start with transversal gates. The first gate that I'll introduce is a transversal left logical multiplication. It's represented as such. I apply LG on all of the leftmost edges of the lattice. The first thing to check is that this commutes with all the stabilizers. It commutes with the vertex stabilizers by virtue of the fact that LG and RG commute. So this vertex stabilizer, they act with RG to the left, LG and RG commute. So this commutes with all the vertex stabilizers. It also commutes with all the plaquette stabilizers. It doesn't create any fluxes. And what I'll argue is that applied to the logical state labeled by H, what this operator does is it takes us to the logical state labeled by GH. You can see that explicitly by considering a nice representative state for the H logical state. LG acts by left multiplication on the leftmost edges with G. So that takes us to this configuration. And by applying gauge transformations to move the G variables to the right, we end up with the state GH. And that illustrates this equation here. Similarly, we can define a logical right multiplication just by acting with the right action by G on all the edges on the right. Acting on a state labeled by H, it takes us to HG bar. So explicitly in terms of a gauge fixed state, a representative state, we take the configuration that has H on the rightmost edges, we just insert G bar. Juice comes from group automorphisms. So phi here is an homomorphism from G to itself. We can define a unitary operator that implements this homomorphism. So it acts on a group basis state labeled by all of the edges. The first thing to check is that this preserves the stabilizer group. It does not commute with all the stabilizers, but it permutes the stabilizers amongst themselves, so it preserves the stabilizer group. And what I'll illustrate here is that at logical level it takes logical state labeled by G to logic to the configuration with phi G on the right. Now let me give an example illustrating how these transversal gates can implement a non-Clifford operation. So consider G equal to D4, the symmetries of a square. I'll represent G D4 as follows. It's generated by A, B, and C. A, B, and C also are to 1. And the only really non-trivial relation here is that if I conjugate A by C, it produces a B. This suggests that D4 can be written as a semi-direct product of Z to A and Z to B. We choose C, where the semi-direct product notation just captures the fact C acts non-trivially on A by mapping it to AB. You know that we can label label the logical states by elements of the group. So any element of the group can be represented as A times alpha, A to the alpha, B to the beta, times C to the gamma, where alpha, beta, and gamma are 0, 1. So this suggests that the code encodes 3 logical qubits. Now we can consider left and right multiplication. We would act left multiplication by with A introduces an A on the left and takes us from alpha to alpha plus 1. So this acts as x1 on the logical level. More interesting, you can consider LC times RC acting on the state, so it inserts a C on the left and a C on the right. We can use the group relations to move the C on the left past A. Pick up a B depending on alpha. So maps this to A to alpha, B to the beta plus alpha, C gamma. That means that this acts as a CX1, 2. It flips the second qubit based on the state even more interesting, so what it does is it takes the element A, maps it to C, B gets mapped to itself, and C gets mapped to A. Now applied to a logical state, and they'll just swap A and C. That's what I've done here. I just swapped A and C. In order to put this in the form where we have A, B, C, we have to move C to the alpha, pass B to the beta, and A gamma. And here's what's happened is gamma have been swapped. Second qubit has been flipped in the state of A and C. So this acts as a swap on the first qubit and a controlled X gate, which with target qubit being the second qubit. This turns out to be a non-Clifford operation. So if we're able to transfer our information to the D4 group surface code, then we could apply this group automorphism to enact a non-Clifford gate, and that would be enough to supplement our Z2 surface code and perform universal computations. Yeah.
In this example, some very specific properties of the default group are used. Then, how do I see how general this is?
What do you mean some specific properties of the D4 group are used?
Like the group structure, not only that you can organize the logical states in this alpha, beta, and gamma way, but also that you are doing it in this particular way, because the usual way I think of D4 is as the symmetry of the square of a square. With two generators, one is the fourth rotation and the other is some reflection. Before seeing your way of writing the group elements, I wouldn't even think of writing the group elements in this way.
I see. Yeah, I wrote it in this way so that we had 3 qubits. But we could use another representation of D4, which is Z4 semi-direct product with Z2. In that case, we also can get non-Clifford gates. Well, I'm not sure. I'm guessing that is non-Clifford. I don't know what happens on the 4-dimensional qubit. I haven't checked this. But in general, when you have this semi-direct product structure, the lowest level here, these act as Pauli operators. When you do left actions, this acts as Pauli operators. These, and the next level, they act as Clifford operations. That's why I have this CX12 here. And then you could imagine adding another layer, and that implements this group automorphism, and that's what does the non-Clifford gate here. So yeah, so this lowest level Pauli operations, and this next level that's defines here. Here I'm doing some inner automorphism, where I'm conjugating the element by the element here, and so that will implement some Clifford gate. And the next level, or using an outer automorphism, goes one step higher in the Clifford hierarchy.
So do you mean you have a general criteria as a surface condition for this framework to work? Meaning if
I don't remember what sort of general statements we can make about semi-direct products, but I would be willing to go out on a limb and say that when you have this semi-direct product structure and it's like sort of a non-trivial semi-direct product, sufficiently non-trivial semi-direct product, then each successive semi-direct product gives you one higher level of the Clifford hierarchy.
I see. Thanks.
Yeah.
Tyler, I have a naive question. I want to know practically, is this useful? Because if we just use 3Q, try to represent the default, it's kind of, we already have the ability to perform this kind of an RG or require a non-clear gate. But in reality, we have natural default QD. So I wondering, it looks like just you try to say the same thing using the other representation, but practically it's still the same difficulty. Like it doesn't help us to apply CCX on the supporting device.
I see. You're saying, yeah, that's right. So if you wanted to measure the vertex stabilizers of D4, you would need to, and you're representing it using 3 qubits, then you would need to implement CCXs.
Right. So it doesn't help us to reduce the difficulty in the experimental device, right?
Yeah, that's fair. Maybe it's a hardware-dependent statement. I am not too concerned about the implementation of the stabilizers at this point, but you're right. Yeah,
Yes, I see. So the point here is assuming we have some already default QD, which can be naturally implemented on some suitable physical system, and using this default system is easier to implement those kind of gate.
well, so yeah, you could use an 8-dimensional qubit and construct this as long as you can, measure those stabilizers naturally on your 8-dimensional qubit. But what I am imagining here is that I have 3 qubits in the system, that LG and RG will look like some product of X's and C naughts. So the stabilizer is still a Clifford operator.
see. But
if you want
Clifford in default sense.
no Clifford on qubits.
Oh, okay.
Yeah. Yeah.
Oh, I see.
Yeah, I can take that 8-dimensional Hilbert space and break it into 3 qubits. And then I can ask, well, what is the representation of LG and RG on those 3 qubits? And LG, I don't know, it depends on what group element I take, but it's either X or X times C naught.
Oh, okay. Yeah, thank you.
Yeah.
If the order of the group is not a power of 2, then we cannot decompose them just into qubits.
Yeah. Well, that's right. Or you can impose some constraint and like turn 2 qubits if you want into a qubit.
So you mean ultimately, even if I, for example, have a qubit, I want to add some constraint to reduce it to a qubit? Or the other way around?
Oh, sorry. I was saying, you were saying if the order of the group is not a power of 2, I can't represent it on qubits. And I guess that what I was saying is, you still can represent it on qubits. You might just not using your resources efficiently. Like I can represent a qubit
Sure.
on 2 qubits if I want to.
Yeah. For example, I'm asking, suppose the group is S3 with 6 elements.
Yeah.
Then using this framework, the number of logical states will be 6.
Yeah.
Then you cannot organize them as an integer number of qubits.
Yeah, there you could have a qubit and a qubit if you wanted.
Then when you talk about Clifford, Clifford meaning what?
Yeah, so I'd have to tell you what I mean by a Pauli operator on a qubit. But this is quite naturally taken to be just a clock and shift operator.
Okay.
Yeah.
Thanks.
Yeah, thanks. No, those are good questions, and there's not much I can say about hardware implementation of these codes. At this point, it's fairly abstract. Okay, I'm somewhat pressed for time, so let me unfortunately make these next steps somewhat schematic. But the next logical operation that I'm going to introduce is an extension and a splitting. This is what allows us to transfer information from abelian surface codes into non-abelian surface codes. And at a high level, what it does is it takes an H group surface code, a K group surface code, and turns it into a group surface code for a larger group. And in general, we can extend H and K group surface codes into a knit product of H and K. If I hadn't infinite product is. But for the purpose of this talk, I'll just consider a semi-direct product. That's a special case. But this is what allows us to extend to non-Abelian groups. For example, we can take a Z2 cross Z2 group surface code and a Z2 group surface code and use this for a desired non-Clifford gate. And then transfer information back into Z2 surface codes. And I'll conclude here just by listing some future directions. Thanks.
So how can I see that this is sufficient for universality? For example, if I want to perform maybe a phase gate, can I see how can I implement this gate using your protocol?
Yeah, no, that is maybe difficult to see. It turns out that, there are some remarkable set of gates that are universal. For example, just a Hadamard and this controlled NOT gate is universal. And that might look kind of that you use something like CCX and supplement that with the Clifford operations, and that allows for universality.
Ah, thank you.
Tyler, I also have a question.
Yeah.
Which you already commented on and Yuan asked. So in the introduction, you mentioned here you are using non-abelian topological phases in certain way, but different from how people previously used to do topological computation. And you said the reason was practically what you do here may be technically easier. Then later, when you answered Yuan's question about practically how easy it is, then you said at the moment you don't really have assessment of that. So I certainly think the ability, the possibility of doing this and the whole structure of
then you can implement some transversal gate if you'd like, or then you can implement some transversal gate if you'd like and switch back. It may be just a way to perform operations with topological qubits too.
For the continuum, you mean the one on Kagome lattice?
Yeah.
Yeah, maybe a related question is, in your description of the topological phase, you are using a particular realization of it, a particular microscopic realization where the local qubits have the basis of the group elements. But in the continuum realization of the D4, each qubit is really a qubit, and it's a D4 of a kind of non-trivial reason. Then really in that particular microscopic realization, would you imagine one has to do a lot more work to implement the whole thing?
In which realization takes more work? What do you?
The realization using just the qubits on Kagome lattice instead
I
of
think
using
that
eight-dimensional
naive.
qubits.
I see. Yeah, naively, the complexity of the Hamiltonian terms in terms of qubits look the same. There's a product of Pauli X operators and some CZs, or product of Pauli X operators and some C naughts. So they look very similar represented on qubits.
So it doesn't matter that the Hamiltonians are not commuting projectors.
Yeah, it's not essential that the Hamiltonians are commuting projectors.
Mm-hmm.
But I guess I don't really know how to assess the complexity of the stabilizers. I guess that's what you're asking about. But at least naively, at surface level, the Z2 cube twisted quantum double stabilizers look very similar to these D4 group surface code stabilizers when represented on qubits.
Mm-hmm. Okay.
Yeah.
Any other questions?
I had a question about your last point about the Hopf algebra.
Yeah, I don't have anything too intelligent to say about this, but yeah.
Just wanted to maybe make a comment. This bi-cross product also exists for Hopf algebras. This kind of like knit product. Wonder if we can just plug and play. Yeah, this is something that mathematicians have studied.
Oh, that's very cool. Yeah, that's nice to know. Yeah, I think this is kind of an ambitious last bullet point here because ultimately what makes the group surface codes nice is that you can relate them to some abelian group surface codes, do some computations in the abelian group surface codes, and transfer information as needed. With a general Hopf algebra, I don't know that you have that luxury that you can transfer information from your Z2 surface codes, for example.
Right. The one example I was thinking of with H8, it's an 8-dimensional Hopf algebra. That can be thought of as a co-cycle version of this bi-cross product. So it's some more data, not just a bi-cross product. You can think of it as like a central extension analog for Hopf algebras.
Yeah.
But you did say that central extension